answers to those few questions that were asked concerning the presentation. So thank you very much. And I wish every presenter all the very best. And those that are participating, I also wish you all the very best. Thank you. So we shall now move now to, can I ask, does anyone want to ask any question, even at this time? Or maybe any observation, any comment? So if we don't have any comment at this time, we'll move now to the first section, which is going to be anchored by Mrs. Uyanga Kindness. So I'm handing over to her right now to take over the very first section. Thank you.
Hello, everyone. Welcome to the first session of the 2020 Association of Nigerian Students in Hong Kong Research Forum on Environmental Science. It is with great pleasure that I usher you all into this 30-minute session, which will include two presentations, one from our esteemed guest speaker, Dr. Afolayan, and the other from our own noble young man, Mr. Blessing Adoti. Dr. Afolayan will be enlightening us on the tropospheric features influencing the West African South monsoon rainfall, while Mr. Adoti will enlighten us on the elements mobility in rock exploration and sharing. And he will be talking about a new approach that can be used to determine shared zones with accurately. So it is my hope that we will all benefit from these two presentations, and it will be insightful, informative, and also a research seed for further work. So I'm sure that this session will be timely. Our first speaker will, as has been said, will present in 15 minutes, while the second speaker has just 7 minutes to present. So since we have a limited time for questions, 3 minutes, please use the link at the bottom of each abstract to ask questions. You can also do that, ask questions using the link while completing the questionnaire to help assess the presentation. So please welcome, relax, and enjoy this session. Dr. Afolayan, you have our attention now.
Can you see my slide, please?
Yes.
Firstly, I would like to say thank you to everybody, especially the members of the organizing committee, for inviting me for this presentation. So I will be talking on understanding the variability of West African summer monsoon rainfall. We look at the contrasting tropospheric feature and the monsoon index, which I developed. So I will try as much as possible to be explicit. So monsoon here is defined as a seasonal reversing wind that brings about changes in atmospheric or climate variable. So in this case, we're interested in precipitation. So if you look at the first figure here, I don't know, can you guys see my cursor, my mouse?
Yes.
Yes, we can.
So if you look at the first figure, if you look at the whole delineation of the global monsoon region, West Africa, which is the focus of this study, falls under the monsoon region. And typically in the northern hemispheric winter, which falls between the month of December, January, February. So you have the northeasterly trade wind dominating the entire West African sub-regions. So the northeasterly trade wind is responsible for bringing dust into the continent. So this period is essentially dry. You have little or no precipitation, except in the coastal parts that you have rainfall. Now in the summer, specifically June to September, June, July, August, September. So you have a trade wind which is originally southeasterly, but upon crossing the equator changes direction to southwesterly. Now, this trade wind is responsible for moisture influx inland. So the entire subregion is dominated by southwesterly flow, and this is the typical rainy season over West Africa. So the seasonal reversal of the wind direction is known as monsoon, as I've explained earlier. And I will also briefly talk about the mechanism that is controlling precipitation, especially monsoon over the region. So if you look at the atmosphere at upper level at about 100, 150 hectopascal, which is about 18, 20 kilometers, you have what we call a tropical easterly jet, which has a source from the India Ocean. So the tropical easterly jet is as a result of the temperature gradient, changes in temperature that exist between the ocean and the Tibetan Plateau. At mid-level, you have the Africa easterly jet, which is more localized, is as a result also of the temperature and meridional gradient that exists between the Atlantic Ocean and the Sahara Desert. So the lower level is what I've explained, is the monsoon flow, which is which depicts the influx of moisture. So overall, you have three tropospheric features controlling the West African precipitation. So you may want to ask, what is the essence of studying the West African monsoon? Now, the region, West Africa in this case, has experienced large fluctuations in seasonal rainfall, and these fluctuations ranges from a wide range of time scale, from intraseasonal, which is critical for rain-fed agriculture, hydroelectric power generation, water resources, to the seasonal aspect, the seasonal time scale, which is more critical for long-term water availability over the region. Now, as I've explained, the region has experienced large fluctuation in rainfall over the years. So notable is the drought in the 70s and the 80s. And of course, the increasing precipitation, which was observed in the 50s and the 60s. So because of this variability, farmers will want to know what is the trend or what is the mechanism controlling precipitation over the region. And as I said, it's essential for hydroelectric power generation, water resources, and overall economic sustenance. So in a way to characterize and quantify the variability of this monsoon, it is crucial to use an objective index, in this case, to measure how it varies. So here we are going to look at a way to use a representative variable, at least to measure the variability of the monsoon. And previous studies have reported that over the West African region, some have said that there's a noticeable increase in precipitation. Some say, yes, there is an increase, but it's not consistent. Some say the increase is not coherent. So we raise a question that what is the recent variability and trend in West African monsoon? And how does the tropospheric feature, which I've explained earlier, the mechanism controlling the precipitation, how do they vary in a typical wet and dry year? We'll discuss about the trend, and can we use the insights from the variability of the tropospheric features to develop a new objective index? Now, previous researcher, they usually develop index based on area average precipitation. This is less common in recent time because of sparsity of high quality ground observation. And some few studies, especially two which have developed index of monsoon based on wind. The first is a whole paper in 1995 by Fontaine, which used the modulus of wind at 900 and look at the difference between the 200 hectopascal, which is the level of the tropical easterly jet, and the surface. And the Unified Monsoon Index in 2002, which is about the dynamical normalized H15 wind hectopascal. Yes, the indices have been remarkable over the years, but they do not capture entirely the dynamics controlling the precipitation. So hence, it is important to improve on this. So I will also give you like a brief insight of the climatology. So the West Africa, which we're talking about, is here. The region closer to the Atlantic Ocean is called the Guinea Coast, followed by the intermediate Savannah region and the Sahel in the north. So if you look at the climatology of the precipitation, rainfall is a maximum over the islands, especially the Futajalon, the Cameroonian, and precipitation decreases northward to the Sahel. So if you look at the evolution of precipitation, around March, April, this is the onset of precipitation in the south, in the Guinea coast. And precipitation progresses northward into the Sahel. So the period you have the maximum precipitation, which is usually in August, you have a break in the Guinea coast and sudden sensational retreat in September, October. So essentially the Sahelian region experienced one peak of rainfall, but in the Guinea coast here, as a result of the break in August, we have two peaks of rainfall. And this is so because if you look at the dynamics, now the summer period we're focusing on, don't forget, this is June to September. Now for the upper level tropical easterly jet, you have the maximum intensity within the summer monsoon period, which is our focus. For the low level westerly flow, you have the maximum intensity in the summer. But the Africa easterly jet, which is at mid-level, occurs throughout the entire year. But in the Guinea coast, when you have the little dry season, you have the maximum in the Sahel. So the variation of the middle level Africa easterly jet is responsible for the two peak of. Now, if you look at the long-term variability of precipitation over the region, as I've explained, so you have the wet period in the 50s and the 60s. This was in well-known Sahelian drought in the 80s and the 70s. And the studies, some studies in recent time, including mine, have shown that there's a recent increase in precipitation. But overall, if you look at the long trend, based on three different graded products, there is a significant decrease, which can be as high as 0.4 millimeter per decade over the entire region. And if you pick the three products and you do an area average trend analysis over individual subregions, so you can see, based on the trend value, a decrease in precipitation. So if you perform, this is a yearly, this is based on yearly analysis. So if you perform a running mean and you fit out, let's say you pick a 5-year running mean, we can see that the interdecadal component dominates the decreasing trend which we earlier observed. So I will also go briefly to the dynamic before we go directly. So how many minutes have I spent, please?
You spent more than half of your time. You have
okay. Yeah, so we're still good. So a caption, the dynamics, don't forget, tropical easterly jet at upper level, Africa easterly jet at mid-level, and low-level westerly flow. So because tropical atmosphere, as a result of the insolation, so is inherently unstable. So at all time, you have air rising into the atmosphere. So if you look at the climatology of the rising motion, you can see an enhancement, increase, that is vertical ascent climatologically. At the level of the upper level tropical easterly jets, you have a strong divergence. So the role of these upper level dynamics is to create upper level divergence to force ascent from the surface. Now, so why you now want to ask, why is this two dynamics very important for precipitation? So the mid-level tropical Africa easterly jet is in maximum at around Senegal 15 degrees north. So you have wind increasing northward. So that creates a cyclonic wind shear. The low-level tropical easterly jet, it decreases southward. So you have the maximum at around 5 degrees north. So you have an anticyclonic wind shear. So this creates a cyclonic overturning, which is favorable for exotic convective system that leads to precipitation. So within the latitudinal bed of these two mechanisms, from 5 to 15, you have maximum precipitation as a result of this condition which I've explained. So in a way to see how the tropospheric features contract, so we pick three graded precipitation product for consistency's sake, and we define a new indicator, multi-data dry year and multi-data wet year. So these conditions are respectively true if all the three graded products have like an anomaly which is below negative 0.8 and 0.8 positive. So with these, we were able to pick about 8 wet years and 8 dry years. And we perform a composite analysis. So this is the composite anomaly of the tropospheric features for wet year, and this is the dry year. So not to waste your time, for wet year, typical wet year over the region, the intensity of the upper level tropical easterly jet, it is stronger than the mean climatology, as you can observe by the easterly anomaly. At mid-level, the Africa easterly jet is lower than the mean climatology, and the low-level moisture depth is deeper. So this is so because if you look at the sustenance of the jet stream, if you look at the climatology of specific humidity and temperature, now the region where they converges, you have the jet maximum at 15 degrees north. So you can conclude that the jet doesn't like too much of moisture and too much of heat. So when the moisture depth is too deep in the wet year, there is a northward shift and reduction in the intensity of the Africa easterly jet. So a reversal is found in the dry year. The upper level tropical easterly jet is weaker than the climatology. The mid-level Africa easterly jet is stronger, and the moisture depth at the surface is shallower. For the ascent, in wet year, you have enhancement of the ascent, and then you have a suppression in the dry year. So based on these insights, we pick an area average precipitation over the region and regress on these tropospheric features. And we observe that they are statistically, the steepings are region where you have a statistical significance of 95%. So we observe that over these three regions where you have this main mechanism, you have, they are statistically significant over that region. So based on that insight, we use a multiple regression to develop a new index. Here we call it West African Summer Monsoon Index. The index is positively correlated and significant with precipitation up to 0.8. Now, if you look at the time series of the newly developed, hello, you say what? Can I proceed?
You have a minute more.
Okay, yeah, so this is like the second to the last slide. So if you look at the time series of the newly developed index in red and also the time series of precipitation, so you can see our index is key to capture the wet years of the 50s and the 60s, the dry year of the 70s, and also the possible increase. So our index is able to outperform existing indices of Fonte 1995 and the Unified Monsoon Index. So conclusion. Of course, there's a notable contrast in the tropospheric feature between a typical wet and dry year. So that for a typical wet year over the region, you have a deeper moisture depth at 850. You have a weakening and a northward shift of the Africa easterly jet and an enhancement of the upper level tropical easterly jet. A reversal is found in the dry year. So based on these insights, we developed a new West African Monsoon Index, and our index is keyed in a way that it was able to capture the observed interannual and decadal variability in the precipitation, specifically the wet years of the 50s and the 60s, the dry years of the 70s. And lastly, a brief insight in the future. So in our previous work, we observed a recent increase around 1998 to 2012 over the Sahel, which is supported by enhancement of vertical moisture convergence. In the future, there will be increasing mean precipitation, enhancement of extreme, and also enhanced rainfall variability. So details you can read in this paper. Thank you so much.
Thank you
So
very
we'll take
much.
any questions you have.
Yes, thank you very much, Dr. Afolayan. Please, we now have the floor open for questions. You can direct your questions now. We can take one question now, please.
Yeah, thank you, Dr. Akintomiwa, Akintomide, I mean, sorry. Yeah, please, I want to ask, like we know about the monsoon condition in the South Asian region, which there is an ongoing debate about its interaction between the mountain building belt, the Himalaya mountain, Now, I want to ask, because since this monsoon is also the same thing that goes on in the Asian region, do we also have any possibility of such interaction in the West African zone? Is there any correlation between orography and the monsoon system in the West African zone?
Yeah, thank you for your question, Blessing. So, as I've shown from the climatology of the precipitation, if you remember that we have the maximum precipitation over the highlands, in the west over the Futajalan, and in the east over the Cameroonian. So orography is very crucial for precipitation. And also the atmosphere, it's like a box. So West Africa is not isolated from East Asia. So you have interaction and coupling. And the upper level tropical storage, which I explained also, has a source from the India Ocean. So you can see one of the system interacting with each other. For example, wet year over South Asia, India specifically, there is also wet year in the Sahel. So, and vice versa, like that. Am I able to answer your question?
Yeah, thank you. Yeah, I feed from it. Yeah, thank you.
Okay. Thank you very much for your presentation, Dr. Afolayan. It is now time to move over to our
Thank you for having me. I appreciate it. Have a lovely forum.
We'll now move over to our second presenter, Mr. Blessing Adeoti. So you have our attention for 7 minutes.
Yeah, thank you, Mr. Moderator. Oh, sorry.
Can you take up the question?
Please, can you all see my screen?
Yes, yes.
So I'm going to be presenting on element mobility as a proxy for defining the width of shear zone for mineral exploration and geoenvironmental. Look, I did it before leaving Nigeria in FUTA. So right now I'm here, and that's why I have my department in FUTA appearing in this presentation. So what is shear zone? From the left-hand side, you could see the box. The shear zone is the region where you have the two arrows showing one going to the right, the other one going to the left. It's just a region where we've had intense deformation of rock. As a result of that, that region becomes so very weak, such that it permits water fluids to move in easily. And as a result of that, it's involved a lot of change in rock chemistry, which are stored within the shear zone, which is quite different from the adjacent undeformed rock. And one other important thing about this shear zone is because during this fluids that pass through this shear zone, they could carry some minerals that are economically, benefit to the society. And so studying shear zone is important. And one other key point about the shear zone is that because it's a weak zone, if things like earthquake is supposed to happen within the region, this site will favor earthquake eruption because it's already weak. That is why it is important to study. I really don't know what is happening to. Okay. It is important for us to really study what the shear zone is all about. In the previous study relating to the thickness of the shear zone, remote sensing method, geophysical techniques, and going to the field, observing rock textures, and also taking samples from the field, viewing it under the microscope, have been the various approach in which we use to study this shear zone to be able to know the boundary. Now, why is it important for us to know the thickness? For example, if you look to the right-hand side, you see an image. This is in Iwaraja in Osun State, Nigeria, and I stood there and I took this picture, and you will see the red line to the right, actually showing where it is assumed that that shear zone terminates. And if you look within the base of the mountain there, you see a lot of built up buildings in that region. So which means that if this is a weak zone and an earthquake is supposed to happen in this region, it's gonna be very, very economically, impactful to the society. Loss of life, loss of buildings, including engineering structures that might have been set in that place. So, and what are the causes, things that may not allow us to really understand this thickness? From field experience, we observe that because you have some inherited texture from the undeformed rock still present in the deformed rock. As a result of that, signals from geophysics or maybe remote sensing, even field studies and thin section actually may not be able to pick that. But in the past, we've been able to understand that this shear zone, since they store chemical elements, and we can look at the construct between the chemical element within the shear zone and that of the undeformed rock, then I think that if we adopt that in trying to map across the shear zone, we might be able to get something that could give us a better guide. For example, in the picture of this Iwaraja shear zone, from previous work in Adelusi et al. 2013 and Adelti, an approximate of 580 meters was actually established for the region where we have this red mark to the left to that of to the right. So in this work, I'm proposing that if we are able to track down on the element mobility within this shear zone, we might be able to accurately define where this shear zone really terminates. And that could really help environmental planning in terms of informing people this is where to go. And if, for example, this region also hosts some important exotic minerals, these are areas where people could be advised to map. So in this study, what I did was to take samples across the shear zone. I have a box here that shows explanation. Can you see my cursor that shows explanation about how samples was taken across the shear zone? And I have about 11 samples taken across this shear zone. One limitation in this place is that my ability to take sample were based on their exposure. There are areas where I should have been able to take, but because of exposure, I couldn't take them. That is a limit. That is one limitation concerning this very study. But then, as we move on, we hope to maybe we have something we could get from it. So the rock samples were taken and analyzed using the ICP-MS method, and below in the table is just a few selected chemical composition that was taken from the rock samples. So in the result, the very first image to the left in the A part shows the texture. This is a micro photo section that was taken under the microscope to see how large or how small the minerals within the sections are. And then if you look towards the eye, which shows as we move into the interior of the shear zone, minerals grains have decreased a lot as a result of the deformation. This deformation, they happened under extreme pressure and temperature. So, and in the result, now I'm trying to look at as we move away from the shear zone, you could see UMP, then UGG in the table to the left. So the UGG is towards the undeformed region. If you look below, you see that I'm about 1,420 meters away from the region which I defined to be the interior of the shear zone, which we already seen where the texture of the shear zone is well seen clearly on the field. So begin.
Your time had ended.
7 minutes ended?
Your time? Yes, please.
Okay, thank you.
Yeah. You can just talk about your conclusion and then.
Okay.
And end
No,
it.
I thought of maybe handling over. I'm so sorry. So, but after taking that analysis, I'll just move on and just describe how. So, obviously, these three, we have the iron oxide, the silicon oxide, the titanium oxide, and magnesium oxide, and the this actually helped us to see that if we take a boundary very close to this region between the P and the UGG, we could actually determine, because as we can see, this little dot shows how this chemical element changes as we move towards the interior of the shear zone. So like I just want to point out that from this result, I was able to determine that about 680 meter, 680 meter is the thickness of this shear zone, which is quite different from the already, what we already know about the shear zone. Thank you for listening. I don't want to go further from this. Thank you very much.
Thank you very much, Mr. Blessing, for the insightful lecture on the rocks. Yeah, please, it's now time for questions. Can we have questions from the audience, please? Any questions, please? Okay. Okay, and since we have already taken some extra time from this session, you can forward your questions to Mr. Blessing using the link shared on the chat feature. Okay, and with that, I will now hand over the session back to the chairman. Thank you.
Thank you, Mrs. Raya Kindness. Unfortunately, I couldn't do very well in this presentation. And I happen to be standing in for the chairman. Oh, what a pity me. Thank you so much. So we move now to the second section, and I would love to hand over to the coordinator. So please just take over from me. Thank you very much.
Okay.